Hello everyone. Today we're going to talk about control systems. So today we're going to try solving a question based on rotational mechanical system. Before solving, we'll just go through the fundamentals quick and fast. So before moving into the fundamentals, let us know what's rotational motion. So rotational mechanical moves are about a fixed axis. These systems mainly consist of three basic elements. Those are moment of inertia, torsional spring, and dashboard. So these three are the components that we are going to use for the mathematical equations or the equations that helps us to form the electrical circuit. So if a torque is applied to a rotational mechanical system, then it is opposed by opposing torques due to moment of inertia, elasticity, and friction of the system. Since the applied torque and the opposing torques are in opposite directions, the algebraic sum of the torques acting on the system is zero. Let us now see that. So now let us see the F5 and FE analogy quick so that we can go through the conversions and then start the question. So Fi stands for force current. Here you can consider torque. Torque is basically a rotational force, so you can consider it as Fi analogy. So these are the respective conversions for each and every component belonging to the rotation mechanical system. So T, torque current, moment of inertia G, C, rotational friction coefficient. This is basically dashpot, and this is spring constant K, angular displacement theta, and this is angular velocity V, omega. So this is the FV analogy. So T stands for V, and moment of inertia C stands for N, and so on. The rest are the other four components. So let us start the question. Write the differential equations governing the mechanical system shown in figure. Draw the torque voltage and torque current electrical analogous circuits and verify the mesh and node equations. So basically, we need to do the TV and TI electrical analogy. So you can see that we have 3J and one spring constant K. No, we have two spring constants K. And this is basically the torque, the arrow mark you see here. This is the torque, or and this is the dashpot B1, B2. So let us start the question. Basically, whenever you solve the question for the questions based on FE analogy, or even it might be translation mechanical system or rotational mechanical system, you need to draw a free body diagram. This helps you to a quick and convenient way to answer. So we need to remember one more thing, that while writing the equation, you need to write a equation with respect to theta1, an equation to respect to theta2, and what are the coefficients that come along with the J1, B1, and K1. So along with J1, it's d square double differentiation of theta, and along with B, it is a differentiation of theta, and along with spring constant K, it's just theta. Here you can see that it's theta1 minus theta2, because we'll go back to the previous page. You can see here that the spring constant K1, it's being shared by J1 and J2. Therefore, K1 is multiplied with theta1 and theta2. Just a small inconvenience. We don't have the theta2 representation over here. So we'll make sure that the circuit diagram is rectified. But you need to remember one thing, that wherever the J is present, there's always a theta present over there. And I think this arrow mark represents the torque force, rotational force, which is torque. So this is the equation form at theta1, which is J1 into d square theta1 by dt square plus B1 d into theta 1 minus theta 2 by dt plus k1 theta 1 minus theta 2. So this is the general mechanical system equation that we have written over here. Now we need to convert this equation into electrical equation. We have seen this. First we'll do go for I analogy or FE analogy. Anything is convenient. So we just need to remember these like replacements or conversions. So if for each respective coefficient or for each let's say parameter, you need to convert it to their respective parameters, electrical parameters. So this is the equation. Now, this is the equation at theta 2, as I said, for each mass, or sorry, for each j, that is inertia, there is a theta acting on it. So this is for theta 2. So this is the equation formed at theta 2. So j2 into t squared, theta 2 by dt square, and so on. You can see the equation over here. And again, since there were three inertia body diagrams, so we'll have three thetas. So this is the third equation formed at theta 3. Basically, you need to write all the components that are connected to the particular theta. So see, these are the conversions. So we'll first go through the mesh analysis or the torque voltage. So L1, you can see that J1 is the replacement of L1, J2 is a replacement of L2 is a replacement of J2, my bad, and L3 is a replacement of J3. So you replace these equations. You can see that this is the first mechanical system, equation we got in uh, the mechanical diagram, which is with respect to theta 1. This is with respect to theta 2, and this is with respect to theta 3. And after the replacement of each equations with the mechanical parameters, which is converted into electrical parameters, these are the three equations we get. Now we have the equations, but now the solution we need to find is to draw an electronic circuit. So first, you can see that the E of t, which is the source of power, is present or is connected, or you can say is linked only with the components of the equation 1. As you can see, there's no source of power on equation 2 and 3. This is one point to be noted. The other point to be noted is that each equation, since this is a voltage analogous circuit, each equation has only I. There's no, this is not a voltage deduced equation. And at certain parameters of electrical circuit like R and or C over here, you can see that it is shared among two currents. So this basically indicates that the resistor or even the capacitor is present between two meshes which have two different current running through it. This is shared or is present between these two current flowing meshes. So this is how you need to imagine and uh, plot the electronic circuit or electrical circuit. And we need to remember one more thing, that you can see that it was d square. This was d square theta by dt square. We know that d theta by dt is d phi by you can see that d phi by d theta, d omega by d theta, which is nothing but di. So you take it as di by dt. So you can see that this is the respective or the uh yeah, this is the respective voltage analogous circuit for the respective mechanical system. Now let's go to the torque current analogous. This is similar to the voltage analogous, but the replacements are or the conversions are different for each component of the mechanical system. So T is replaced with I of t. One more thing which I forgot to say is you can see that in this equation As I said, E of t is linked or connected to only components of theta 1. You can see in this circuit too that while plotting or while writing this circuit, E of t is connected only to the components which are linked with I1, which is current 1, or the first mesh. Similarly, the torque is replaced with I of t, and the other respective, these are the respective replacements of each components of mechanical rotational system. Again, you can see that this is what the equation will have, the three equations after the conversions. Similarly, we had d square theta by dt square. So d theta by dt is nothing but voltage according to the torque current analogy, and hence we have dv by dt. So we can see again that R is shared among two voltages. Here, inductor is also shared among two voltages. So these resistors and inductors are present between two node voltages, and that's how you plot these two components. So this is the respective torque current analogy circuit. So basically, this is a simple concept, but the only thing you need to remember is the proper respective differential equations that come along with the components and the right conversions um, for torque voltage and torque current analogy. So that's it for this video. Thank you.